All right, and we are back Monday morning. Good to see you. Hope you had a good weekend. Weekend right before test one. Test one is testing center today and tomorrow. Closing time tonight, I think, is 7. Is that correct? And closing time on Tuesday is 10. Double check that though to make sure. Okay. Um, Make sure you go in at least an hour before the closing time. That's good form. And I've heard that the line conditions are okay. There is reduced capacity in there, so you should be able to get in and out okay, and with distancing and everything in there. So I think we're good to go. You can take models in there, but make sure they're in a clear plastic bag. It can't be anything solid that you can have notes or any paper in there. The test is, of course, closed book and notes. So that's what they're worried about. At one point, they actually told us we couldn't allow any models going into the testing center, and our department fought back against that and got that reinstated. The compromise was okay, a clear plastic bag. That's the whole story there. You can have cyclohexane all ready to go, or butane, whatever you need to do. You know, they can be together already. So that can give you a head start. If not, a lot of people are fine on a piece of paper. If they can see those 3 dimensions, they're okay. You don't have to use models. I don't require it, but it can be useful that way. But yeah, using your scratch paper is probably the best advice strategy for taking the test, okay? That and considering all 4 possible answers on the multiple choice. Don't latch on to one answer right away. Make sure you look at the 3 other ones first and consider all aspects of it. There can be elements of truth in one or more wrong answers. So look for the best answer that fully answers the question. That's another good strategy. And you guys have taken a lot of multiple choice exams. You have strategies for that. But yeah, slow down, use your scratch paper, experiment a little bit, and consider all the possibilities there. So yeah, whatever. Chapter 1 through 4. We'll be starting chapter 5 on Wednesday. Stereochemistry coming up there. Today is all review. Couple topics here at the end of chapter 4 that I just touched upon, and we'll sell a little bit more with the overheads. Let's do chair cyclohexane first. There's a couple things to review there. And, you know, the simple idea is having a substituent on cyclohexane and, you know, orient yourself, you know, and start with maybe the flat view of it, right? And so that's a good step there. To see, you know, that methyl group is up. Here's the flat view, and then we can pucker, you know, the sides up and down. It doesn't matter which side you do as long as you're consistent there. So if we pull this one down, you see that's what? The methyl is in a equatorial or axial position. Equatorial, right? You should be getting pretty good at that. So you can see that the axis is here, the hydrogen there is in the down position because this carbon's puckered down, okay? So that down position on a down carbon is going to be what? Axial. And you can see there. So we can do the ring flip, push this end up and this end down. And, you know, you get to this where now the methyl is what? Axial. What about the equilibrium here? Which side's going to be favored, the left or the right? The left, right? Because that puts the methyl group in a less sterically encumbered position. The axial position, more sterically encumbered, has the 2 gauche interactions, and plus that methyl's closer to these 2 axial hydrogens. So, you know, make sure you've made a connection physically with the models, right? Here's our methyl group, equatorial position. If we flip over to the axial position, the axial equatorial positions all around the ring exchange position, and that has some consequences. This is closer to these diaxial hydrogens here. You can see the gauche interactions there and there, whereas they go away here, okay? It's anti-staggered over to there. All right, let's look at one here that's a little more complicated. And this is Decalin. We told you the common name for that. And it's a fused bicyclic ring where 1 hydrogen's up, 1 hydrogen's down there. you can look at the flat view of it, or you can just go right to the chair here. You see one chair is there, one chair is there. We'll see that structure in steroids here in a minute. That's transdecaline. And this is actually locked in this position. If you try to ring flip this, you've got some problems. And let's do it. Let's ring flip that. So just looking at this ring on the left here, what happens to the ring on the right side here? So now we've got this. And that is this ring here trying to accommodate these two hydrogens now in equatorial positions with the ring fusion coming off diaxial. If you do that with your models, you can't ring flip the transfused decaline because this can't accommodate the ring size to be diaxial like that. Okay, so there's some limitations here. But what about the cis-fused decaline, where the two hydrogens are up? Now, this is an advanced topic. I've never put this type of problem on the test. This one's a little hard to see. But I think going through it helps you review some of the concepts here and seeing, what the transfusion would look like and how that constrains actually these two rings. They're locked, we say, in the chair conformation that's shown here. But the cis one's a little bit different. Let's view this where we can see this cis fusion. So one of them you see is axial, one is equatorial as I've drawn it there. Okay. And now we can look at a different view of this, rotate around just a little bit. If we rotate this whole object by about 60 degrees and then look at it like this, it looks like we ring flipped this ring on the left, but actually we changed the position of where we're looking at the other ring there. It's actually the same thing. Here's our axial hydrogen. And let's keep track of that one, okay? So we've got that axial hydrogen there. Everybody see that? I just rotated that object around. It still has the two hydrogens, cis to each other? And the ring fusion carbons coming off that are still cis to each other. Okay. Yeah, and drawing these are a little tricky there. But let's focus on that circled hydrogen that we've got, axial coming off this ring right here. Okay. And let's try to flip this thing. So if we flip it, what will it look like now? Well, let's take this carbon down and this one up here. We'll get this view, which will have this in the back. Okay. And now you see our hydrogen here is equatorial. Okay. Was axial, now it's equatorial. And this one here that was equatorial relative to this ring is now axial to that ring. Okay. And, and that looks kind of funny. We can't really see the chair conformation of this ring. This looks kind of flat. And same with our first view here before we kind of rotated the thing. But this is where we actually flipped it because this went from axial to equatorial. Okay. Now that is tricky a little bit there. And let's rotate this guy again by 60 degrees. And then what you see is this. And then you can kind of see the two rings, both in both with the chairs readily available. And then that hydrogen right there is the one that's still equatorial relative to this ring here. And this one's that axial one that we started out equatorial relative to that ring. But you can see the two chairs easily there. So cis decaline, the whole reason I'm pointing this out, is it is conformationally flexible. It can ring flip fine and go back to two nice chairs. Whereas the transdecaline, if you ring flip either side, you'll force the other ring that's fused to it to try to accommodate this diaxial arrangement, which it just can't do. Physically, it's just not big enough. There's not enough distance in those bonds, we say. But anyway, this is an advanced topic. This is a tricky one. But if you can do that with your models and go through it, especially with the cis one, that can be a nice review for you to see that. Okay, so we'll see cyclohexanes all over the place, including the world's hardest material. Now we think of organic compounds as, of course, being covalent, soft materials, low boiling points, low melting points. But ironically, if we extend the cyclohexane indefinitely through 3 dimensions, guess what? We create the world's what? Hardest material. And what is it? Girl's best friend? Diamond. Very good. Someone always does it. Okay, let's see if we can extend this here. Okay. I always mess up some of these. Oh, there they are. Okay, we got a few going there. Yeah, you get the idea. Keep doing that through 3-dimensional space there, and that is diamond. Okay, it's all carbon. It's carbon-based material. It's a mineral. It's mined out of the ground. Why is it so strong? Well, it's all carbon, covalently linked, right? sp3 hybridized, and it's this extended network of 3-dimensional space where you have in 1 dimension the cyclohexanes all fused like this, and then this dimension there's a whole other set here and a whole other set on this other face of the material, and it's kind of a neat extension of what we've been talking about. All right, let's go to the overhead here, Jashurin. Let's see what we need to do to finish off. Let's see, chapter 4. And they do have this redox idea here, oxidation, increasing the number of Z bonds or hydrogens. Oxidation, decrease the number of carbon-hydrogen bonds. So if you're adding oxygen to a molecule, that's oxidation. Z, oxygen is a typical Z one, but Z also can be what, nitrogen or halogens, or taking away hydrogens, okay? Reduction in OChem means decreasing the number of Z bonds, taking away oxygen, and or adding hydrogens, okay? Now the inorganic definition of oxidation and reduction is what? Think of metals, right? If we take electrons away from a metal, we form cations. Okay, so that's loss of electrons is oxidation. If we add electrons, we're what? Reducing the oxidation state. And there we clearly see charged ions, right? But in OChem, we have covalently linked things. So we talk about the increase in the number of oxygen and or the decrease of hydrogens within functional groups. And you'll see the functional groups down here in a second. Or reduction means what? Taking away oxygen and adding hydrogens, okay? So what do we have here? Here's the most reduced form of carbon, CH4, which is methane gas. We've been talking about that. That's the most reduced form we know of. If you oxidize this, add an oxygen in between one of these bonds, we create methyl alcohol. So what have we done? We've added an oxygen. We haven't taken away hydrogens, but by adding an oxygen, we've what? Oxidized methane to methanol. If we take away 2 hydrogens here and put the pi bond on there, that's formaldehyde. If you go from an alcohol to a aldehyde or ketone, you have to take away 2 hydrogens conceptually. That's also oxidation. So everything here going to the right is oxidation. Add another oxygen in between this carbon-hydrogen bond. That's a carboxylic acid now. There's 2 oxygens there. It's almost fully oxidized. We take away the last 2 hydrogens, then we get to the most oxidized form of carbon. That's the end of the road for carbon, by the way, CO2. Then it's a gas into the atmosphere. Is that it for carbon? If we oxidize carbon dioxide, combustion or whatever, metabolism, our bodies were exhaling more CO2, right? Is that the end of the road for CO2? No, what do plants do with CO2? They convert it back to reduced forms of carbon, sugars, okay? Plants make sugars from CO2. And then we eat those plants, whatever, and we reoxidize it back up. So carbon's actually in a cycle. It's constantly being oxidized and reduced. But we can keep track of that from these functional groups here. So we'll look at a couple functional groups and then say, well, which one is more oxidized or which one's more reduced. Now, this will have importance when we look at reactions later on. So don't worry about this concept too much right now. There is a hierarchy, though, of functional groups as far as which ones are more oxidized, which ones are reduced. So what's the most reduced form of functional groups we've been talking about? Alkanes, right? Okay. And then the more oxidized functional groups we've been talking about carboxylic acids. Is CO2 a functional group? Well, yeah, but it's just that simple molecule, right? The fully oxidized form of carbon. It's the most stable form of carbon also, by the way. So CO2, yeah, kind of the end of the road there. All right, alkane combustion. We talked about this briefly. We showed you this, even though we had the epic failure with the butane balloon, right? The gas blew out the torch and it didn't ignite. Yeah, we'll have to revisit that sometime. Butane makes a very large fireball when it's properly combusted anyway. But here's the alkanes, right? Methane, ethane, butane, and then some of the other ones here. Some of the branched ones too, showing you what's going on. Boiling points, very low if they're small, of course, or if they're more branched, they're a little bit lower. So like isobutane versus butane, look at that. So isobutane has a lower boiling point, right? And then the heat of combustion, what's this? Oh, this is in kilojoules per mole. I prefer kcals per mole. That's what most organic chemists think about. A calorie is the amount of heat needed to raise 1 gram of water 1 degree Celsius. So there's a physical connection there. Actually, the IUPAC, the SI unit is joules, not kcals, but it persists. Most organic chemists and biochemists use kilocalories. So what is this? The heat of combustion. When this combines with oxygen, it makes that much heat. And we can measure that accurately with bomb calorimetry. Okay, there's a combustion chamber. It's surrounded by a known amount of water, and we know the heat capacity of water. So you can measure the temperature of that amount of water after that material inside the bomb combusts. So it's a relatively simple experiment. And what you see, this can be very accurately done. Butane, the straight chain one, look, gives off a little more heat. It gives off 2 more kcals per mole, minus 688 versus minus 686 for isobutane. So actually, there's another factor here. The boiling point goes down with branching, and if it's branched, we say there's more like bonding. There's a methine carbon here with 3 carbons on it. That's actually more stable, okay? So it actually gives off less heat, okay? The less stable one is actually the straight chain one. The more stable one is the more branched one, so it gives off a little less heat. And that carries over into octane, the octane rating, straight chain octane versus isooctane. Isooctane has the lower boiling point, right? The higher octane rating, but it actually gives off less heat, less power. But because it combusts quicker, more efficiently, the engine overall runs more efficiently. So kind of some strange things to look at here. But what you also notice here, it's a tremendous amount of energy, 1,000 kcals per mole for hexane, and it's up around 1,200 kcals per mole for octane, right? This is a huge amount of energy. So the more carbons you have, the more energy you have generated. Why is that? Because there's more CO2 being formed. So let's balance a couple of those equations maybe here on the board. So yeah, it depends on what the formula is, how many carbons you've got there. Let's balance the simple one plus oxygen. You've done these before. I guess to fully balance it, we need to say the energy that's liberated here, right? So how do we balance this? Well, the carbons are already balanced. So always do carbon first. There's 1 there. Add it in if you need to. How many, and then always do hydrogen next. So there are ways to keep these straight. Hydrocarbon combustion equations are this way. Always balance the carbons first. We just have 1 carbon there, so 1 there. How many hydrogens over there? On the left, we got 4. So how many oxygens, or how many water molecules are we going to generate? 2, right? 2 times the 2 is the 4 there. 4. So we're balanced there. And always do the elements last. So the single element oxygen, leave that to the end. And so how many oxygens do we have here? 2, 3, 4. So how many do we need here? 2. Okay. So methane doesn't generate too much products here. 1 mole equivalent of CO2 and 2 water. In the excited state, this is high energy, a lot of thermal energy generated that excites the electrons to a higher orbital state. And when those electrons decay back down, it gives off a photon of light. That's what you actually see the flame. Okay. So everything's actually in the equation here. How about this one? Same thing for propane? No, always draw out the formula. So what do we have here? C3H what for propane? Remember the general formula for alkanes? Cn what? H2n plus 2, right? So what is this? 8, right? And there they're all. 1, 2, 3, 4, 5, 6, 7, 8. Everything goes back to the structure. When in doubt, examine the structure. There's good advice for you. Okay, so what are we going to? Still CO2 plus even more heat now. What do we balance first? Carbon, so 3 there. Everybody see why I put a 3 there? Because the empirical formula for butane is C3. So yeah, we're already generating more CO2, more heat. Okay. And then what? Do the hydrogens next. So what do we need here? We got 8 over there. So what do we need right here? We need 4. And then how many oxygens do we need? We've got 6. We've got 10, right? Total. So what do we need here? 5. So yeah, it's going to require more oxygen. You're going to have to feed that flame more. That's what it means engineering-wise. You have to make sure it's ventilated well. Okay, should we do one more maybe? Oh, how about butane? So see if you can balance that one. And you know, the isomeric forms, isobutane is still what? C4H10, right? So you have the same balance here, but a little bit different heat, okay? If it's more branched, it's actually more stable, gives off less heat, okay? More like bonding, we say. So what is this, 4? So we need a 4 there. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do we need here? A 5. And look at those ratios change, right? 4 to 5, 3 to 4. Actually, Lavoisier, the very famous French chemist, in the late 1700s, measured the relative amounts of water and CO2 coming off combustion. And from these ratios, he deduced what the empirical formulas were of different compounds. That's the transition, Dalton and Lavoisier, from alchemy into chemistry, something we could actually measure and put some real scientific basis to what's going on. He and his wife built these very intricate devices, chambers that could keep track of the amount of liquid water. He'd condense the water, and then he'd check the volume of CO2 coming out. So for the late 1700s, he was an amazing guy, Lavoisier, Antoine Lavoisier. Unfortunately, he was a tax collector for Louis the 17th or 16th. And during the French Revolution, what did they do to Lavoisier? They chopped off his head with the guillotine. So that's what you get for doing science. No. Okay. That was a joke. Sorry, I guess that's not funny at 8 in the morning, especially losing your head over these equations. Don't lose your head over test 1, okay? So what is this? So let's balance the oxygen. What do we got? 8, 5, what's that? 13, 13 halves. Is that okay to do that? Some chemists don't like to see the fractions here. We'd have to times everything by 2 to get the ratio. I'm okay with that, okay? And it is this absolute ratio anyway that's the important thing, that's different anyway. And then the amount of heat. Anyway, is that enough on that? Don't worry about the mechanism of that reaction. It's very complicated. We're not going to do the mechanism. Very exothermic, a little spark or a little electric discharge will make that material combust, as long as enough oxygen is present, right? So there's some things there. All right, let's go back up here, and then we'll get to sample tests. Sorry. Alkane combustion, anything on there else? Okay. Hydrocarbons, CH compounds, are in the lipid family of biological materials. This is why we study alkanes, not just for fuels, But acyl triglycerides are triesters. So, kind of review your functional groups here too, which was what, chapter 3. So a glyceride, this is glycerol over here, and then there's esters of it. So these are esters now. Okay, there's no alcohol or carboxylic acid here. And the R group can be very long. Okay, 16, 18 carbons long. They're not soluble in water. They hang out in adipose tissue, specialized cells in the body, fat cells. Wax material, those are produced by different spots in your body, your ears, for example. Again, long chain esters here, not soluble in water. Fatty acids, if you form the conjugate base of this, the carboxylate salt, that's a soap material, forms those micelle vesicles that can solubilize grease and different dirt. Fatty acids can also have polyunsaturated positions or multiple alkenes. So there's another functional group, arachidonic acid, has 4 alkenes and 1 carboxylic acid. Upon injury, the body converts arachidonic acid into these molecules. These are prostaglandins that control the biological response to that injury by dilating blood vessels and bronchial tubes to allow specialized cells of the immune system to get into that injury site to begin the healing process. A lot of times the body overreacts and you get chronic inflammation, which can be a problem, pain and soreness, swelling, whatever. There are certain drugs, NSAIDs, non-steroidal anti-inflammatory agents, including aspirin, that control the production of prostaglandin. We'll say more about this pathway when we get into some of the other functional groups and what some of those drugs are. But you should be able to look at a molecule like that and identify what? The functional groups and something about the properties. Okay, so that's all we're expecting you to know now. Squalene, an amazing polyene molecule here, very nonpolar, is converted into cholesterol. Okay. Liver cells can do this. You produce a couple grams a day. And cholesterol is not just a bad molecule. It gets a bad rap because different diseases are correlated with high levels of serum cholesterol, right? Your LDLs and HDLs, you've probably heard about those tests. If there's too much serum cholesterol in a bad form, which are what, the LDLs, the low density lipoproteins, that can lead to occlusions within small vesicles, especially around the heart, can lead to heart attacks and whatever. Okay, let's look at the lipid bilayer membrane then. We need to say something about where cholesterol is overall. Because actually in your body, you're only producing a small amount per day, and you get some from the diet as well. Most dietary cholesterol passes right through you though. It's the stuff that's made in the liver and then packaged in the less water-soluble particles, the LDLs, that are a problem. The high-density lipoparticles actually are more soluble. They're smaller. They tend to go through the blood without a problem. It's the LDLs that are a problem. And they need to deliver cholesterol all around the body to go into the lipid bilayer membrane. So here we see the phosphatidylcholines, which are the main component of the lipid bilayer membrane. And this is the nonpolar long chain here. And this is the choline part, the charged part, which is on the outside of the cell and on the inside of the cell. And this is the barrier here, the interior of the membrane. And what are these little molecules right here? There's one right there and one right there. Oh, it's labeled for you. Cholesterol. There it is. Most cholesterol in the body is interstitial. It's inside the cell membrane. What does it do there? Here's a model of cholesterol. What do you see? First of all, my hand's holding the only polar group. It's one single alcohol, right? And then the rest of it's all hydrocarbon. It has the topology of being what? This kind of linear blob, which is nonpolar, okay? And it's about the same length of just 1/2 of the total distance across the membrane. So this polar group presides what, on the exterior up toward the part exposed to water. And then this is in the interior. Well, what does it do? It disrupts the packing forces of the phosphatidylcholines. If you did not have cholesterol in the membrane, it would solidify at room temperature. We'd all freeze up. Okay? This is part of the fluid mosaic model you probably heard about in biology. To keep the lipid bilayer membrane fluid and mobile at room temperature, you need cholesterol. And it's quite a bit, quite a high percentage. I think it's 20%. So in your body, you have many hundreds of grams of cholesterol. Okay, luckily not in the serum, not in the blood, because it would precipitate out and cause clogging problem. But if it's in the membrane, in this interior, you see it helps balance that fluidity and keeping it mobile. So it has a very important function there that's kind of cool, I think. Anyway, enough on lipids. I'm doing too much here. Okay, make me stop. Yeah, okay. Let's go back to the sample test and see what we need to know there. I'll just kind of go through it briefly. If you want to stop on some specific ones, feel free. But I will go to the board in a second and do some of the harder problems, I think. And a couple of you have emailed me already, and so I'll help you out there. But if you're here live, feel free to chime in. And if you want to email me later, if you're watching the video, that's fine too. And of course, we have office hours tomorrow and recitation sections. So, you know, take your questions to the TAs also tomorrow. But let's go through it here a little bit. So first page there, I don't know, a lot of definitions, a lot of things structure-wise. When in doubt, go back to the structure. Remember things like formal charge, hybridization, you know, draw those structures out if you need to. Use your scratch paper, experiment with these type of problems. This first one there. Electropositive atoms, you know, it's just the opposite of electronegative. Okay, they can readily lose electrons, so I think that's C there. Bond angles, yeah, that's just simple realization of hybridization, right? Knowing some of the structures. This azide anion, nothing organic there, but azide anion, you know, you can count up electrons, make sure you start with the neutral form of nitrogen in that case, which is 5 valence electrons, right? We're only showing valence electrons, so the 5 ones there, got to count them up, and then formal charges, right? So this nitrogen in the middle is plus charge, and then the ones on the ends with 2 lone pairs, that's the actual structure. And you're given the overall negative charge of azide, N3, okay? So there you just need to pile them up and make sure you count electrons, okay? And then you'll get to the right formal charge. MO theory, yeah, just the simple basic bonds. So make sure you know what a sigma bond looks like, which is this one, a sigma star where they're out of phase, and then a pi, and then a pi star, okay? So those are the simple ones. Yeah, question. Yeah, we'll draw that one on the board, and we'll go through a couple more artwork things here in a second. Let me just go through this briefly. People ask about pKa's all the time. They want me to give them a big long list of all the ones they need to memorize. I'm not going to do that to you. I think that would be cruel and unusual punishment to make you memorize a bunch of. But look at the structures and think about what the stability of the conjugate base is going to be, right? Carboxylic acid, that's one you know, 5, right? Alcohol also has an OH group, but that conjugate base is a negative charge just on a single oxygen, not on the 2 here. So this has resonance to stabilize that one more. But phenol is more acidic than a typical alcohol because it does have resonance stabilization. It's 10. There's another one if you want to memorize phenol. Feel free. I won't require you to, but I think you look at the structure and the resulting conjugate base and see that D is a stronger acid than that one, okay? And then if it's just on a carbon, that resulting carbanion, it's not as stabilized as O minus, right? So always look at the structure. So you can rule out A and B there, I think. D is the correct answer there. Same thing down here, select the weakest acid. Well, that would just be the hydrocarbon one. The carboxylic acid, the strongest one, and then the field effect with 3 fluorides, lower that pKa even more. So again, I'm forcing you to look at the structures, and that kind of helps you keep track of it. And then definitions of methyls, methynes, whatever, that's fine. Same thing here for the pKs for the reaction indicated. Yeah, this K equilibrium constant is very large, right? It's 10 to the 4th power. So I showed you how to estimate there, and here I give them to you. Those are 2 I told you to memorize. Why did I give you those numbers on that one? I don't know. I guess we're nice. We're trying to help you out there. The most stable form of this isomer would be the one that has strain-free rings. If you have too many small rings, that raises the energy of that molecule. And when a small ring compound combusts, it gives off a lot more heat. than a strain-free structure, okay? Relationship here, those are the same thing. They're just ring flipped to each other, but double check these. These are both 1,4 and equatorial. Those are trans to each other. And if you ring flip, it's axial. Yeah. So these are what? These are conformational isomers, C. So some definitions there, yes?
So what's the difference between a conformational isomer and a stereoisomer? I thought stereo meant the same molecule as well.
Conformations, we've actually rotated around a sigma bond. So what's the difference between a stereoisomer and a conformational isomer? Conformational isomers involve rotations around sigma bonds, okay? So ring flipping, we're actually rotating around these bonds on the side, okay? These are still trans 1,4 dimethyl cyclohexane. The stereoisomer would be cis 1,4 dimethyl cyclohexane. And that would have a different position here for that. Okay, does that answer your question? And we'll draw here in a second. We've got time to do a couple of quick. Let's get to that. Identifying functional groups. These are single functional groups. There's an ester, okay? This is not an ether and a ketone, okay? If you have an oxygen next to a carbonyl, that's an ester. It's not a ketone, not an ether, okay? There is an ether here. It's right there, that methyl ether, okay? There's no carbonyl next door. If there was a carbonyl next door, it would be an ester. Here you got a ketone with 2 carbons next door. That's a ketone. If it was a carbonyl with a hydrogen and then a carbon on the other side, it would be an aldehyde, okay? So make sure you know the specifics of functional groups and what they mean there. Question?
So if we had a question like this and there was a phenol, would we lose points for labeling it as a benzene and an alcohol?
No, yeah, phenol. Yeah, that's kind of a specialized alcohol. Yeah, we'll try to be lenient there, but if it's an ester and amide, there's definitely things there. All right, let's go to the board and do a couple of these. And I've got the worksheets too. Yeah, come over here, Jeshurun. Let's see. Which one do we want to do first? Oh, I like this one. 1,2-difluoroethane. You're told it has a significant dipole moment, pretty large, okay? 2.5, in fact, right? This is problem 2. So this kind of combines this thing about polarity, polar covalent bonds, and what conformations. So it kind of combines a couple ideas here. Draw the low energy conformations here. Well, we have to look at some Newman projections. Put our eyeball right here, right? Remember what a Newman projection is. You're told you got to draw a couple Newman projections. That would be 1 Newman, right? Staggered. Maybe that's the low energy one. Let's see, we could rotate this guy around here and have this one. What? This one's anti the 2 fluorines, right? 180 degrees. What about here? This one's gauche. Can you assign a dipole moment to that molecule in the 2 different conformations? Now, these are interchanging, okay? But you're told when you measure the dipole moment of difluoroethane, it's significant. And then you're asked to determine which conformer do you think is more favored. So there's some analysis here to do. What's the dipole moment of this? They're opposite of each other, right? Directly opposite. So overall, that dipole moment, you'd say would be nonpolar. They cancel out, okay? What about here? The direction of these dipole moments are enforcing, right? So that would give a strong overall molecular dipole moment. Now, which one do you think is dominant, or which conformer do you think is responsible for this polarity? Well, it'd be the gauche one, mainly, okay? And so even though this might be minor, there's enough of it present at equilibrium to make it what? Significantly polar. It turns out this is the major one. It's like 60-40. It's not the sterics. Fluorines are pretty small, okay? It's actually a sigma-sigma star interaction you can look at. That's an advanced deal. But this one you need to recognize there's a significant dipole moment, and that contributes to the overall observed dipole moment for the molecule. Question on this one, yeah?
Wouldn't the eclipse only
Yeah, but the eclipsed one would have higher energy with everything eclipsed. Okay. Yeah. Yeah, the staggered ones are the ones that most of the time they're at. So someone is asking about the eclipse conformation of this being even higher, and that would be true. Okay. But because it's eclipsed, that would be less percentage-wise the molecule. But yeah, you had to recognize something about this having a significant dipole moment. Because since it's drawn here, look, those cancel out too. Just looking at the drawing. Anyway, yeah, I don't want to spend too much time on this, but yeah, quick question on it. We got 60, 120 would be eclipsed. So it's the 60 and the 180 that are staggered. So yeah, someone's asking about an eclipsed one at 120. And again, that's a higher energy one. We could look at that, but yeah, these are the significant ones. All right, let's look at number 3. Draw a clear picture of acetylene. And we give you an empirical formula of acetylene, so it kind of helps you remember something about what acetylene is. You know, you may not have memorized that common name, acetylene. What's acetylene? Oh, welder's gas, maybe? Or what is that? Well, what type of bond are we going to have in acetylene? Well, carbon-carbon bond, hydrogen's on the end. And then what do we do in the middle here? Oh, it's a triple bond, right? Okay. He wants us to draw a 3D structure of that and include all the bonds and label everything, okay? So kind of the first part of these is figuring out what we want you to draw, right? Everybody see going from C2H2 to this? That's indeed acetylene. So what are we going to draw here? Well, we've got the sp hybridized framework here. We've got the sigma bond here, and then pointing over here, another sigma bond there. So there's 2 sp hybridized molecular orbitals coming off that carbon, right? So we've mixed the s and one of the p's to make the 2 sp orbitals. So that's the sigma bond framework. Sigma, 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 okay? Localized on the axis. What else do we have, though? We have the 2 other bonds between carbon, and those are the leftover p atomic orbitals, right? So we got this one here and here. And draw the shading, you know, the sign of the wave equation. They're coherent there. They're in phase with each other. So what do we have? Both top and bottom, that's a pi bond, okay? In phase. Is that the only one? No, there's 2 pi bonds for acetylene, right? And so give it a little dimensionality. Be a little bit of an artist. You'll be a lot better than I am, I'm sure, but this would be the other pi bond here. And you know, take up the space. Draw it nice and big so we can clearly see it. If the grader has to look in there, well, maybe label the sigmas and whatever. And make sure it's linear, you know, the thing here. Anyway, any questions about the artwork or the MOs or anything there? Okay. Yeah, okay. So, yeah. Okay, isomers. I like number 4 here. Draw all the isomers for C6H14. Number 4, C6H14. Ouch, and it says all the isomers. And name them with the IUPAC rules. So what are we talking about here? This is indeed what? C6H14. So that's what molecule? Hexane, right? So start with the linear one, and that'd just be hexane, okay? And then how do we do the isomers? Lop off a methyl on the end and put it on branching, right? So the next one would be this one. And that's what, 2-methyl hexane? I won't draw the whole things out, but the first one is hexane. 2-methyl hexane. And these are constitutional isomers now, right? These are not stereoisomers. These are constituted differently, okay? We have this position here, and now it's over there, okay? Yeah. Oh, very good. Thank you. Someone just earned some extra credit here. Catching another one of my many errors on the board. Not hexane now, right? The longest chain here is indeed pentane. Thank you. Okay. All right, how else can we do the 3 position there? We can do that one, and that's 3-methyl pentane. Okay. Can we move it over again over here? No, that would be 2-methyl pentane again. So, so what do we do? Well, let's try a butane, maybe with 2 on there. And that would be what? 2,2-dimethyl butane now, right? And then is that the only way to do that? How about this? That would be 2,3-dimethyl butane. And is that it? From that chart, you can see there's 5 possible ones, and I think we've got them all. Can we have it just a propane and maybe put the 3 on there? Would that be one? No. Now we have carbon with what? 5 bonds? That wouldn't be right. And the wrong number of hydrogens. So there's some limitations there. So we get to the end there, and that's it. All right. Let's see. We've got a couple minutes. How about some of the worksheet problems? Somebody was asking about those. Anybody have one they'd like me to go over? Yes, please. Uh-huh. For which one? So, what's that? Okay, problem number 6, the multiple choice. Okay, yeah, let's look at number 6 here. Oh, okay, yeah, let's go back. Somebody's just asking about number 6 and drawing the orbitals. So yeah, what would the orbitals look like? So whatever the hybridization is, if we have carbon with that orbital coming in, there's 2 different ways we can do this. We can have them in phase with each other or out of phase. So if they come together in phase, we'd have this. And so that's on the axis there. So is that a sigma or a pi? That's clearly a sigma. And what would the sigma star look like? Well, that's where we'd flip one of these around, right? And we have carbon look like this now. And then make sure the phases are different there. So there's a node actually at that position. So that's no longer a sigma, but it's localized on the axis. It's still a sigma something. But being out of phase with an extra node there, and we call this what? Sigma star. Okay. And then same thing with the pi's. They come from p atomic orbitals. If we bring them together in phase, we have this arrangement. So we call that a pi. Okay. And they actually can touch there, right? We have, that density above and below, but it's off the axis, right? There's actually a node right at that position for pi's, for p's, right? So that's just one. What's the other one if we bring them together out of phase? It'll look like this. They actually push back from each other. That would be out of phase. Where there's an extra node here now, in addition to that node. So that would be what? The pi star, or the anti-bonding pi bond. Pi star. Yep. Okay. And the relative energies, this one's the lowest one, being sigma density. Then this one, okay? And the next one up is actually this, okay, because it is off the axis. It's a little bit lower in energy than this one, which is a super high energy one, the sigma star. So being able to draw those or recognize it. Notice this says nothing about what the hybridization here. At least you have to have sp2 or sp hybridization on the carbon to invoke a pi bond. But the sigmas can be from anything, sp3, sp2, sp, okay? So we could draw more there. Yeah, and we're out of time. Bring more of your questions to recitation or my office hours tomorrow, or shoot me an email, and we can always respond that way as well. But I think we're fine. Good luck on the exam. You'll do fine. Use your scratch paper. Carefully consider all the answers on the multiple choice before you latch on and bubble in that one answer. Look at all the possibilities there. And we'll see you on Wednesday here in class, chapter 5. Read ahead, and we'll see you then. Thank you. Okay.